Hello, everyone. Thank you, everyone, for joining this webinar, Improving Processing Stability Using Dynamic Simulation. My name is Anas Syed, and I'm working for MSc Consultants Limited in the IT team. I will be coordinating all this webinar with you. Before we start the webinar, I would like to share some tips which will improve the webinar experience. During this webinar session, all the attendees will be muted to enable the speaker or the presenter to have a proper audio to be heard by you all. Please check your speaker phones in your computer or laptop or in your mobile devices to have a better sound quality. Now, if you are viewing the webinar screen very small or medium, you could maximize them by pressing Alt and Enter keys together. That is Alt and Enter keys together. If you press them, your screen will be maximized. You can post your questions or any issues using the chat window. The chat window you can access using, if you hover your mouse around the top of the window in the green bar, you see the chat icon, which when you click the chat icon, you see the chat window being launched. You could post your questions to MSc Consultants Limited. Now, we'll have a Q&A session towards the end of the webinar where you can post your questions through the chat window, or you can get in touch with us later. We'll share our contact ID towards the end of the webinar. Now, let's get started with the webinar. I thank everyone who's tuned in for this webinar, Improving Processing Stability Using Dynamic Simulation. Now, I'd like to tell a little bit about MSc Consultants. Probably many of the people who have joined us, who are our existing clients, knows about us. But any new persons who have joined us, MSc Consultants has been providing engineering consultancy and training services to the oil and gas compression systems for more than 25 years. MSc Consultants Limited is an independent consultancy group. We have offices in Leatherhead and Aberdeen. Apart from the engineering services, we also have developed an array of software tools which we use in-house for our engineers to deliver the projects. And we have also successfully sold software outside MSc for the external clients. Now, if you want to know more about the software tools that's available commercially from MSc Consultants Limited, you could visit our website, msc-consultants.com, and view the necessary software that you'd be interested in. Now, today's agenda is listed as it is in the slide. We'll have an introduction followed by a case study from two of our speakers, and then final remarks. Before concluding, we will have a question and answer session where you can post your questions, and the speakers or the presenters will be able to answer your questions. Now, I'd like to invite the two speakers who will be presenting this webinar to you. The first speaker will be Dr. Marco Musino, Specialist Rotating Machinery Engineer at MSc Consultants Limited. Marco is a study manager and the technical lead for MSc Consultants. Dr. Marco has experience in compression systems, gas turbines, field development, performance testing, performance monitoring, power generation, and structural analysis. Our second speaker for this afternoon, or for this webinar, is Sabir Mahmood, who is a lead process engineer at MSc Consultants. Sabir is a specialist in steady state and dynamic simulation for MSc Consultants Limited. Sabir has experience in compression system performance, modeling, and optimization. He is also got diverse knowledge in both greenfield and brownfield application. Sabir has an engineering degree in chemical engineering from Imperial College, London, UK. So I would like to welcome Dr. Marco to present his slides from here. Thanks.
Hi, hello. Good afternoon, everyone. Thank you for joining us in this webinar. Basically, what is what we're going to talk about for the next half an hour, 40 minutes, is a problem that is commonly found in oil and gas operations, but that is most of the time kind of not addressed because of its complexity, and that is instability. Production instability, it may be considered that, well, systems are unstable in their own nature, and you can't do anything about it. But what happens when this instability comes at a price of production capacity and system reliability or equipment reliability? So we think that if you address this, then you would have some benefit, some operational and business financial benefit to address this. And one of the reasons why sometimes it's not, as I said before, it's not addressed is that it's very complex, and you usually need quite a few set of skills to be in place or onshore, offshore at the facility at the same time to be able to troubleshoot the problem. And so what we have done and what we are presenting here is a multidisciplinary solution to the problem that is bounded together by MSc Dynamic Simulation expertise. So the dynamic simulation, it takes from our expertise and knowledge on all the different areas of knowledge and engineering that you can see. That you need to know about the compressor and surge control. You need to know about process control, process engineering, turbo machinery. You need to know performance testing, performance evaluation, and of course instrumentation that you can see what are what is the information that you're looking at. And the benefit that will come from following this approach into a simulation environment is that basically your real-time operation is not disturbed during the analysis phase. The solutions that are tested in the simulation environment for implementation, and therefore you can test different options, and you don't have to really suffer any upset to the system and maybe trip the process. The need for a very cumbersome testing procedure is also reduced considerably, so you don't have to get into to allocate a lot of resources into building these testing procedures before going to the facility to test it. And coupled to that, obviously it reduces direct cost for this testing, because obviously you have to mobilize your people, you have to mobilize your employees, but you may have to mobilize third parties coming to help you with a trial run. So we see that taking this approach could be quite beneficial for the clients. So we have a case study to share with you of an asset where we actually follow this approach and were able to troubleshoot their operations and then propose meaningful modifications, improvements that would actually unlock production capacity, and it would help with the reliability of a particular equipment that they had experienced some problems with. One of the most important aspects of this type of work is that the way that we are using here dynamic simulation is in a way that it relies quite a lot on how well we can align the model to the real-time operations, and it is a challenge in itself. But we have, as I said, we have come together with different types of skills and all that to be able to develop these models to then troubleshoot the problems. So, without further ado, the asset is the asset overview is an offshore facility. It's an oil production facility using enhanced oil recovery techniques. So it has gas lift injection and water injection. It has 4 well clusters, 3 production separators. It's a 3-stage, two identical compression trains with 3 stages, all driven by motor, and they are fixed speed machines. And so the problem that they were facing is, as many other facilities with identical or parallel operation of train, is that the flow is not evenly distributed between the 2 trains. In this case, there was a split of around 50 to 40%, but also there was an observed high flow instability during the operation, that ranged from plus and minus 10% from the mean flow. Obviously, the throttle and the anti-surge valve were fluttering or with constant opening and closing. The production was limited by the motor current controller, and they had some historical reliability problems with the motor windings failure, and also actually we were told that during the study that tuning was quite difficult to achieve for the system. So this was the picture that we were facing at. Total was something around 90 million cost of production, but as you can see, train 1 was taking most of it, and train 2 was really like the slave train. And another thing from this graph is that train 2 showed more instability than train 1, but then if you add both together, then the overall instability at the discharge manifold was quite substantial. So what did we do? We created this model, and one of the most important things about this model is that we actually modeled the whole system. So we didn't just stop at the throttle valve and the suction and the compressor discharge, but we actually included the gas lift recycle. We included the feed compositions from the different well clusters, so that we were able to simulate for different operating conditions and regimes, the composition of the gas would change depending on which cluster will be flowing, and that of course will affect the conditions of the compressor suction, both composition and pressure itself. And we also included other fuel take-off and of course in service compressor performance. So if you can see, the model is was really quite complex, and this is very simple schematic of it. And the challenge was then first to align it to properly replicate what was being observed in the field. And I think we had a few iterations before achieving that, but it's just kind of that's the way it is, and that's why it's a challenge. But at the same time, it benefits a lot, as you will see in the next few slides. Obviously, we had to simulate the compressor control in more detail, especially the load sharing controller that clearly wasn't really doing what it was meant to do. But the question is, was the controller actually doing what was designed to do or not? And was it enough to do it, to split the flow evenly? Well, clearly it wasn't. But we had to evaluate if the controller was actually doing what it was designed to do. So in this diagram, from this diagram, what you can take away is that you have the master controller that is taking the signal from the both load sharing controllers for the trains, but it's also taking signal from a pressure controller on a separator and also a current limiter controller of the motor. So it is quite a complicated architecture if you think about that. Every compressor section obviously has to be maintained outside recycle, but at the same time working with a load sharing controller. So on a simple diagram, it is clear that it's a complex control system that we were facing, where you had 3 masters and 1 slave. And we all know that when you are in that situation, the slave is always going crazy. You can't really expect that he knows exactly what to do, when to do it, and the orders from the different controllers were sometimes contradictory, just one after the other, and so that all kind of contributed to the instability. Now the other question, and this is the graph on the left hand side, is that whether the control system was actually doing what it was meant to do. And because the TACS load sharing controller that was installed uses or tries to maintain the same distance between the anti-surge line to the operating point on the map for both trains. But if you have dissimilar performance for both trains, then even though that you have the same distance from the operating point to the anti-surge line, you would actually obtain a different pressure ratio across the compressor train. So that means that in this case, train 1 that has more pressure available will always try to suck more gas from the suction manifold, and the train 2 will be left with just the gas that is available. So the only way that works is that basically the third valve will have to come in to try to stop the anti-surge valve, the recite going into surge sometimes. Then surge valve will open, and then the load sharing will obviously become disconnected. It will try to compensate, and it's just a cycle. It just starts with that. But we'll see all these details in the next few slides. But this is one of the main messages that I wanted to take, that when you have a very complex system with a lot of signals and also maybe upstream conditions, it's very difficult to actually identify the problems, and so that's when the dynamic simulation approach that we take comes quite handy. Now I will give the control to presentation to Sabir Mahmoud, who is been here in this study.
Hello everyone, thank you Marco. before I start, I want to just add on to what Marco was saying earlier, how it is not one sort of issue that causes an instability in the process, but a multiple of other issues. And before we can actually model systems to simulate what the real life conditions are, we have to take a few approaches. First, we do take out the design data and then look at it as designed as the model should be, and then we compare it with data, operational data, so that we can align a model to get a sort of an understanding about how the model is going to work. So before we, how do we align a model? We have, for that, we need to get operational data for relevant operational data, but also relevant operations. We have to understand how many modes of operation that particular plant goes through. For this particular case, we have two distinct modes of operation. On most of the time, the operations are in parallel, and they utilize both trains for the production capacity, but at times they do use single train operations as and when required. So let's get into what we have at the moment. This is the first step that we have to take. So our initial issue is to figure out why is there so much instability in the data. The first graph, the first two graphs, the graph at the top actually, is that with load sharing active. The left-hand side graph, it shows the signals from the throttle valve, and the right-hand side shows the discharge flow from both trains. As we have, as Marco explained earlier, that they have a dissimilar flow going through each train, even though they have load sharing active. So this is one of the issues that we have to figure out why it is. So that is when we did performance analysis of the compressors and came up and figured out that the two compressor trains have historically had different performance and therefore could never match flows through the conventional load sharing method. Then we wanted to see if that was the only contributor to that problem. So we took a chunk of data during when they had enough production. The facility had enough production that they did not need load sharing. So essentially, the two graphs on the bottom gave the same values, throttle valve position and the train. The load sharing, the signal is at 100%, so the load sharing in effect is not active. But you still see that the two trains, as you imagine, because of dissimilar performance, has two different. As the train 1 takes more flow than train 2. But the thing that I want you to see from this picture is that how the range of instability is slightly lower from the second case than from the first case. Although there are still instabilities in the process. So from the second bit, we got an idea that the anti-surge control system for this process was actually not tuned well enough to be able to deal with the internal instabilities of the system. The train 1 having high performance does draw a majority of the flow, and therefore in this situation what we call the master train. And the train 2 automatically becomes enslaved, and what ends up happening is that the train 1 is operating at above capacity flow while the train 2 goes into recycle, and this is something we do want to avoid. So this is what we took out from the first bit of this data. For the second bit, what we did is we know that there is two modes of operation, so we have to look at both train 1 and train 2 while they're operating at just single train mode only. What helps in this situation is the fact that because it is operating in single train mode, there is no load sharing active. It has enough flow to sustain the whole train, and therefore it doesn't have to be recycled. So automatically, the throttle valve and the control interactions have been reduced by two different elements. Well, the only thing that is active in this case is suction pressure override control on the throttle valves, which is also controlled by the master controller, like Mark explained earlier, and the power limiting controller. this is going to be a little more accurate when we look at the next slide. But what I want to explain here is the slide on the left. It shows the pressure and the throttle valve position, while on the right it shows the current and the flow. During single train operation, both trains usually are operated with exactly the same amount of wells running when they are operated as single train operation. However, because train 1 has always had more head, a better performance, it can draw more flow. What ends up being, like with the same amount of wells running, train 1 does have higher production, but what it ends up happening is it keeps on constantly hitting the power limit. So the approach was always to have the similar sort of wells running when they're both a single operation to make operations slightly easier, but this is one thing that was neglected during that process. We did the same observation for train 2, and as you can see for the train 2 operation at single train operation without load sharing, same sort of a concept as train 1 with the same amount of wells running. The main difference is because of the performance, it is much more stable and it has a lot less instability and hits the overcurrent limit much less compared to train 1. It's because that's the amount of wells for a single train operation is pretty much optimal for the operation on a single train mode. However, because there are still overcurrent events, so we needed to find out what is contributing towards that overcurrent event. That is when we came up with the conclusion that there is well slugging, and we did clarify that with the operators and with our clients to find out if that is indeed a case. And they did come back and say that, yeah, because they have like deep well tie-ins, and therefore they do like momentarily have slugging operations. So now that is all good. So we have all that information that we got. Now this is what we are going to use to actually build a picture for ourselves and to better understand and align to what the operation is, like what the system is doing in real life. So what we did is we took the real data. We obtained the data from Pi, and then we compared it without taking the assumptions that we made through these data. We built our HYSYS model, and we compared the data against each other. So this is just a table showing the difference, average difference during the model. But I think the next slide will probably make a much better sense. The graph on the left shows the actual Pi data that we were trying to align our model to, and the one on the right shows the aligned model data. So with the assumptions that we have taken and with what we thought was actually wrong with the system, we have been able to model exactly what the system is doing. So this is actually not an easy process. You have to go through different iterations, and you need to understand what are the contributing factors and hone into the major root causes of the problem. Because essentially, if we get our assumptions wrong, or we do fail to see some of the events that is happening, the model will not align. So this takes a lot of going through the data, trying to realign and align the model to come to the understanding. But what it does is helps us in troubleshooting, because once we do align the model, and with the assumptions that we have taken, it gives us an idea, a pretty specific idea, depending on which level of alignment we are at what particular stage. We can narrow down exactly what are the contributing factors for any sort of instability or the root causes for any sort of other accompanying factors when there is a process issue or a controller issue, or in terms of a performance issue for that matter. So now that we have, well, this is more of like a recap, if you would. What we were given in the beginning was a problem statement. The client came to us, told us what problem they were having, and usually it is pretty much in terms of we have an unstable process. Our control system is not tuned. stuff like that. But it is much more that goes into understanding why it is not tuned or why there are having instability. So now that we have gone through all that process, so we figured out, we pinpointed the sources of the instability. The primary being well slugging operations is something that we can't control. It's a natural fact of any process, and the only thing that we could do is manage it. And with a properly troubleshooted process, it is actually not that bad. It will not cause additional disturbance, and if you there has been operations where this has been managed very well. The second thing that obviously we found out, that the anti-surge control system was not tuned properly to the demand of the process itself. And frankly, because there's 3 different stages of the compressor and 2 different trains of compression, and the overall interaction between the trains, it makes it really difficult to try to go offshore and try to play around with the control system, try to tune it. It is easier to do this on a model-based environment so that you actually have a starting point to go and start tuning the process and a systematic approach rather than just trying to do something blindly. When a system is this complicated, it is very unlikely that you'd be able to get any sort of proper tuning if you just went and tried it offshore. And then the third issue that came up is the throttle valve. The load sharing movement isn't working properly because it is, the conventional method requires the 2 compressors that are operating in parallel to have the same performance. And because the compressors were not of the same performance, actually it was vastly different. And there is no way that the load sharing could ever achieve equal distribution of flow. All the 3 factors together, like in terms of process, they don't actually add to one another. They multiply one another. It makes it worse. It's a more of a compounding effect. And so therefore, that is what, the first slide is what the whole picture was. Very unstable, very, very unstable operation. So now that we've figured out what the problem is, what do we do about it? How do we go about trying to fix the problem? The first thing is very clear. We need to come up with a sort of a methodology to be able to tune the anti-surge control system. So the thing is, the client has told us in the past that there were multiple trials of people coming in trying to tune the anti-surge control systems, but have not been successful. It's because of the complexity that was inherent within the whole design of the control system. And we face exactly the same sort of problem when we're trying to model, when we're trying to tune it from our dynamic model. So we needed to come up with a strategy, that the way where we could tune it and try to actually break down why individual components and what are the operations required so that we can optimize a sort of a setup in which we can tune the system properly. First and foremost, we have to tune train 2 first, because with the current load sharing methodology, train 2 acts as a slave instead of actually working in it for proper load sharing. And so most of the operation, unless it is in single train mode, it always operates in recycle and causes extreme instability in the system. We also found out that each train must be limited to a maximum of 45 million steps. The number here is not important. The whole idea is that so that we do not have interaction of the motor overcurrent. So we limit the production slightly during the tuning operation. This will amount to a compressor suction pressure, which is around 3.7. Around, it has to be less than that. That makes sure that the suction pressure is not reached. And then we have to put that throttle valve, like the load sharing controller, on manual for the tuning processes, because we do not want the load sharing to interact while the 2 trains are being tuned. And so the way we go ahead for tuning is we found out the best way to go the most optimized way to tune would be to tune the IP section first, then LP and HP. It might sound like, after you know it, it might sound very relevant because the IP is pretty much the loose link between the two other sections. And if you try to do a conventional tuning method where you try to tune the LP, IP, and HP in a chronological order, it doesn't work. It's because the system, both upstream and downstream, are unstable. And if none of your stages are actually tuned, you could never achieve any good level of tuning for any one of the stages. So therefore, this was the only way we could tune it properly. And we also came up with tuning parameters so that we could actually, when the tuning exercise is done offshore, they do not have to start with a blank slate and go about it blind completely. They have, the tuning parameters we came up with were fast enough to make sure that the compressors never surged, but also reasonable enough to make sure that the controller, there is no hunting between the controllers on the different server controllers. So what I just explained, and this is what we actually did in our simulation model, and this is the only way we could tune the research control systems ourselves. And you see how it gradually decreases the instability. And the first graph A, is pretty much what we showed, the alignment graph, and then how we went ahead and got alignment proper tuning for, and came up with the tuning parameters. So it's basically a slide that shows that. Then again, after we did this, there's two other things that we did. We proposed a modified load sharing control logic, but before we did that, we wanted our whole idea, or our whole effort was to make sure that we could unlock the production capacity of the compressors and we increase the reliability. So for the short term, we suggested that the throttle valve the load sharing is put to manual, and we proposed the percentage open for anti-surge, the throttle valve for each string during parallel operation, and which we figured out, which we came up with by simulating the model itself. And then in future, when there is time and when there is going to be a prolonged shutdown, we could implement the actual, when this could actually be done automatically. So we modified the logic of the load sharing controller. And the logic that we suggested is based on the export meter reading, which is a signal that is fed to every single one of the controllers anyways, but at the moment, at that moment, was not actually used to do anything. So what it does is it takes out the difference in performance out of the load sharing logic, but it actually uses the physical flow that the compressors would see. So therefore, if the compressors have different performance, the position of the throttle valve accounts for that loss of performance, and therefore it gives it a more reliable sort of load sharing, more evenly distributed load. So we just did not come up with the logic. We actually tried it out as well and simulated it. So on the first, the top graph is on the left is the top graph position, and on the right is the loads of the two trains. You can see it's we tried tuning it. The system is much more stable, but we could never get it to load share because of this vast difference in the performance. But then when we tried out our new modified logic and we came up with the throttle valve positions for that logic as well, you see how the two trains, actually it's not just one line, one train operating, its both flows are pretty evenly distributed. So the thing is, we have all this in concept and we did talk to the client. So our next stage is to prove that this concept is not just an academic sort of solution. So we actually have to do this offshore. So the whole objective of going offshore was to implement the test procedures that we wanted to do to see that what we are suggesting is a viable option and it will help. And what we expected is to make sure that the trains do operate at more even flow, reduce, and the thing is that would actually end up reducing the load from train 1 and giving it to train 2, therefore both will operate much further below the motor current limit. The motor has had high winding temperatures for train 1 because it has always been hitting the power limit for a long time during operation. And if we do end up evenly distributing fluids, the motor winding temperatures will come down. It does increase the reliability of the motor windings, the motor, the train itself. And we increase the load on train 2, therefore bring it out of recycle and basically not waste energy in recycling a train where you have enough load to actually operate 2 trains in parallel. So on the very right are the normal operating conditions. The most important thing that I want to point out here is that during normal operations, on average, it is sort of a slow split that they observe. When we went offshore and we did for extended amount of time, we actually tested it for extended amount of time, we were able to bring the flows very, very close together. Although this is an average, the flow after a lengthy period of time was actually much better. The other thing that you can see here is that the winding temperature has come down and the sharing between the load between the trains are much more evenly shared. And that was the objective that we wanted to achieve when we went there. And which has actually, now that it has already been in place, so it has been implemented. So now that pretty much comes towards the conclusion of what I was trying to explain. So I'll just, before I hand it over to Marco, I would just like to kind of quickly recap where we started with and what happened. So the thing that we started with is you have unstable operation with 2 trains having undistributed flow. Load sharing is always having problems with the anti-surge control system, and they are causing extreme instability in the system. There were unforeseen other disturbances in the system that we figured out that was caused by well plugging operations. And they also said to us before that during single train operation, the system seems much more stable, and we identified the reason why it was much more stable. And so I'll leave you with the recommendations of the study, which we just talked about. I'm going to hand you over to Marco, and he will take you to the rest of the presentation. Thank you very much, everyone.
Thank you, Sabir. So just to kind of wrap up, final remarks that we have is that the value that we were able to bring using our dynamic simulation in existing assets is that taking a multidisciplinary approach and expertise, it will allow us to test the solutions without affecting the production and the process. So the risk is highly reduced. We were able to develop a confident approach to develop a model that reflects the process before troubleshooting, therefore increasing the relevance of any potential solution. With this, as I said before, you reduce the amount of resources that you have to allocate for develop test procedures, to do trial tests. You obviously have to reduce production, and if you can't, then the test will be either canceled or extended, and so that will also reduce direct costs associated with this test and the final commissioning per se. Although we are only talking about testing, it will also help the commissioning, because you can, as Sabir mentioned, you can provide some guidance during tuning or the control signal manipulation, control architecture that will kind of expedite the process. This we have used this similar approach for other applications that we actually looked at the validation or modification of the startup and shutdown methodology for another existing asset that was basically coming back from redevelopment. So they were bringing a new cluster of wells. It was a tie-in into the compressor that was modified, and so we actually simulated something like that. And as you see, the compressor and surge protection. We also did apply the same methodology for a flare gas recovery system for the compressor, with very good results as well. And similarly for pump systems, because we not only work with compressors but also pump systems, we were able to do some very valuable troubleshooting involving the recycle valve sizing, wear, replacement, etc. So it's quite interesting. We are planning to do another webinar in a few weeks' time. So if you have any particular interest of any topic that you see there or any other, you can comment that on the chat window, and we will see what is the most popular, and probably take that on the next time. So yeah, thank you very much for your attention, and we're starting now the questions and answer sessions. I think.
Yeah. Hi. Thanks, Marco. Thanks, Sadiq, for your presentation. Thanks all everyone who's joined in for this webinar. Hope it was useful for you understanding the problems in dynamic simulation. Obviously, it's a complex topic. Next 5 to 10 minutes, we'll open up the session for the question and answer. The way it works is you need to send the questions through the chat window. The chat window you could find hovering your mouse to the top of your screen on the green bar. Click on the chat icon, and then you can post your questions to MSE Consultants Limited, and we will answer the questions. One of our speakers will answer the questions. We'll also share our contact details with you, so that if you have any kind of complex questions or difficult ones, we'll get in touch with you offline and email us. So yeah, I'll open the floor for the question and answer session. You can send us the questions. So there is a question from Kadir. He's asking what data in general is required to do such evaluation.
Thank you, Kadir, for your question. The data required is very problem specific. It depends on a multitude of things. So, but in general, we would start with the design data of the process that you are trying to troubleshoot as well, and then take operating data from during your process, so that we do what we just explained, go through that systematic approach and try to troubleshoot.
Yeah, like for example, we'll be both having compressors, maps available, files, data sheets, some high data, and maybe some information about the information that is included in a blowdown report to have the dynamic side of the system. So it's yeah. In general, that would be the information that would be needed.
Does that answer your question?
Thanks, Kadir. Just wait for a few more minutes to see if there's any questions. But anyway, I'm sharing the contact details on the screen for Marco and Sophia. You can contact us if you have any kind of questions you still want to ask us. Or you could visit our website, mse-consultants.com. Use the contact us form to get in touch with us.
Maybe one thing I wanted to just come back and say, like from this list of other cases that we have had across it, if you have some interest or inclination for a following webinar, we will be happy to consider it. You can either post it here or send us an email. It will be quite helpful for us to focus on something that you're interested in.
Just to add on to one other thing that Kadir has said, that I do agree with you. Data sheets are easily available, but site-specific data does acquiring it is sometimes a bit problematic. What we have done in the past, we have gone through all the PNIDs and PFDs and specified the signal data that we require and send it to the offshore engineer. Or at times we have actually got access to their historian, which is SPI or something, so that we could actually gather the data ourselves, the data that we require, and try to build our model so that we can simulate what the problem is happening in the future, or what we can expect of how to solve the problem in the future. So we have done both methods. It's different projects. Like I said, it depends on the client. It's like client-specific thing as well.
Yeah, in some cases, actually, this is one very important thing. We did spend actually some time talking to the operators of the platform, because most of the times they have quite a lot of information and knowledge, and some of them have been there since the first day of the facility. So they are a very good source of information that we will definitely, and we have using for every single study that we have conducted. So we try to do the best with the information that we have, and I think, but this is kind of the beauty of this, that you have a model. If you know about the system and the fundamentals, you can do some assumptions and see if that is exactly what is happening and working. And so it takes some iterations until you get it right. And in some ways that you don't have all the information available, but by using a model, you can try and try so that you can align it to what you're seeing. And if it's not what you're seeing, then you say, well, okay, that assumption didn't work. We can try another one, and then at the end, it also helps the client to kind of, this is like a cross-pollination of information between us and the client, and at the end of it, they come out of it more knowledgeable about their system.
Yes, Kadir, we are recording this webinar, so I'll probably send you an email probably later next week once we process the video so that your colleagues can view them. Yeah, I think if you don't have any questions, we will stop the webinar here. But as you see in the screens, you could get in touch with us, both Marco and Shabir. Marco can be contacted at marco.news.
Okay. Yeah. Yeah. Thank you, Kadir, and we'll be in touch soon. And thank you for joining us. Thank you for your time and attention.
Thank you.